right. Hey, welcome back, everybody. My name is Mr. Roll, principal and teacher, and over here I have Miss Frank, our third grade teacher, and we are in our second week and on day 2. So we're in week 2, day 2. Now, we don't have any announcements for you today. I feel like Richard Nixon here with the twos. Anyway, we don't have any announcements for you here today, so we are going to go directly into our pledge and joke. Go ahead, Miss Frank.
Why did the child want to do his schoolwork on the airplane?
I don't know, Miss Frank. Why did the kid want to do the schoolwork on the airplane?
He wanted a higher education.
Because it's in the sky and it's an airplane, right?
Right.
Okay. All right. Go ahead. Take it away.
Place your right hand over your heart, please. And let's say the Pledge of Allegiance. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
All right, thank you so much, Miss Frank. Let's go ahead and get to it, folks.
Bye.
Bye. All right, hello, ladies and gentlemen. This is the agenda for every day this week. So I just put a little infinity sign on the day, and so I will probably just drop this little clip into the beginning of every day. So every day, I hope you're doing well. Every day, I hope that you are staying healthy, and every day, I hope that you're doing your homework. All right. Anyway, let's get to the lesson. All right. Oh, no, the thing, I set it up. Okay, ladies and gentlemen, we're on week 2, day 2. We're talking about current events and economics. I am standing in Miss Kimmy's classroom because Mr. Barbero, hey, Miss Kimmy. Mr. Barbero kicked me out because he had some stuff to record, which is okay. So if you hear a mysterious voice behind me that sounds familiar, it is Miss Kimmy. All right.
That's me.
Yeah. All right, so we're doing current events. All right. Yesterday we did a review of everything we talked about last week, okay? And so today, let's take it another step further. So we were talking about things that cause economic contractions, because as you already know, and you should know, economic contractions begin for a reason, okay? Economic expansions don't just end. There's always something that ends them. And so let's review a couple of reasons for economic contractions. Reasons for a contraction. And we're starting with the main one that we are dealing with right now.
This
of course,
is very
we have
timely,
disease.
Mr. Roll.
Oh yes, it's current events, Miss Kimmy. So reasons for contractions. The number one thing, right, that we are putting on this list is disease, because that's the reason that we have right now. Okay, and then of course we have war can cause contractions. We have natural disasters. We have a giant catch-all that covers a whole number of things, and we just call that irresponsibility with money. You like that? Yeah.
Well, not really, because that's probably me when I was in college. So, yeah, my father would agree with that.
I know Miss Barbero was watching our last current events as I was filming it, and she was like, so the stock market. I was like, irresponsibility with money. And she was like, oh, that makes sense. She's like, that's a really good catch-all to describe all of the different things. Let's see, I think we had one more. Disease, war, natural disasters, irresponsible with money. Oh, trade imbalances. Trade imbalances can lead to contractions. Okay, so these are all the things, right, that would cause a contraction. Now, today, let's talk about some symptoms of contractions. No, these are, give me 1 second. These are causes of contractions. Let's talk about symptoms of bad contractions, okay? So symptoms of recessions or depressions, okay? symptoms of recession or depression. So, when we talk about symptoms, kids, symptoms are not the ultimate cause. Okay, symptoms are things that happen after the thing is caused. So, if we talk about symptoms of a cold, okay, if you have a cold, you get a runny nose, okay, maybe you get a fever, okay. Today, if you get a fever, be careful, okay. But when you get a cold, the runny nose doesn't cause your cold. The runny nose is a symptom of the cold. So you have the runny nose because you have a cold, all right? And so these are symptoms of recession and depression. They don't necessarily cause the recession or depression. They are caused by the recession or the depression. But here's kind of a weird thing about this, kids. These symptoms of recession and depression can actually make the recession or depression much worse, okay? In science, we have something called the greenhouse effect. Okay, where the warmth of the sun hits the earth and it makes Earth this wonderful place where we can all live. But as we emit greenhouse gases into the atmosphere, those rays from the sun, which normally come and warm us up and then are bounced back out into space, are trapped inside the Earth, and it makes us too warm. Okay, and so that would be the greenhouse effect, where something that is normal and natural actually comes back and it pushes things a little bit too far. And so some of these symptoms of recession and depression can actually cause recessions and depressions to become worse. Okay? All right, so symptoms of recession and depression. Okay? Number one is a shortage of money. A shortage of money. Shortage of money. All right, folks. Now, the really highly paid professors of economics and the people who are business experts, they cause this shortage of money a liquidity crisis or a liquidity crunch, okay? And this is what we're going to focus on for the rest of today. This first symptom of a recession or depression is a shortage of money or liquidity crisis. So when a recession or depression happens, okay, people are often reaching for their money, okay? They might be selling stocks. And so in class, before we were locked down, we talked about what a stock is. A stock is an actual ownership in a company where you own a small piece of that company. That company is yours, but only a very small percentage. And so in a recession or a depression, people need money to buy things like food and medicine and pay for their shelter. And so they reach for money in different ways. And so they sell their stocks and they sell some of their possessions, okay? So they get more money to pay for things. And so one of the things that we see in a recession or depression is that we don't have enough money, okay? Now, in order to fully understand this, we need to discuss the word liquidity. And liquidity is going to be our next vocabulary word, okay? So the next word that we need to talk about today is liquidity. Okay? Now, liquidity is a weird word. When you hear the word liquidity, you should be thinking of water or liquid, okay? And that's where that word comes from. The word liquidity describes the ability of something to be bought or sold. If something has a very high liquidity, it is very easy to buy or sell it, okay? If something has a very low liquidity, it is very hard to buy or sell it. The more liquid something is, the quicker it can be turned into cash money, okay? So liquidity describes, okay, let's see, it's on a little bit of an angle here. Okay, so liquidity is how quickly something can be turned into cash money. Okay, so let's talk about things that maybe are more liquid, okay? So something that would be more liquid would be really easy to sell. And when you're talking about liquidity, you're usually talking about things that are more expensive, okay? We're not talking about a bag of Takis, okay? When we're talking about liquidity, we might be talking about a used car, okay? Now, most used cars actually have high liquidity. It's easy to sell a used car. In fact, there are services where you can go on the internet and you can type in the exact model of your car and the condition that it's in, and they will offer to buy your car immediately, just like that. And so used cars have a very high liquidity, okay? They're very easy to turn into cash money. Now, there are many items that don't have a very high liquidity, okay? Specialized equipment has a very low liquidity. So I know some of you are interested in becoming scientists and doctors and things like that one day, okay? And so specialized medical equipment has a very low liquidity because it's very, very specific, okay? If some of you kids grow up and become scientists and you have a medical or scientific imaging machine, some of these imaging machines are only found in a dozen places around the whole country. And so buying one of these imaging machines might cost $1 million, and if you need to sell it, it's very hard to find someone who wants to buy it, okay? So these things have a really low liquidity. Some other things, like cards, if you collect baseball cards or Pokemon cards or something like that, okay, those cards have a very high liquidity. It's very easy to find somebody online who's willing to buy them, but then other things don't have such high liquidity, okay? A collection of used underwear, okay? That has a very low liquidity because nobody wants it. It's very hard if you have a large collection of used underwear and maybe you have 2 million pairs of underwear, but they're all used for some reason. Maybe you ran like a rental shop for a sporting goods or something like that and you want to get rid of it. It's very hard because it has a very low liquidity, okay? And so in a recession or depression, we have trouble with liquidity, okay? There's not enough money to go around for everyone, all right? And that is one of the symptoms of having a recession or depression. Now, today's lesson was confusing. Maybe you're not connecting the dots as to how these two ideas relate to each other, and that's okay for now, okay? You don't need to have a good understanding of how a shortage of money relates to liquidity in a recession or depression. We're going to talk about that tomorrow. But for today, I just need you to understand these concepts. Concept number one, in a recession or depression, one of the things that happen is we have a shortage of money. Concept number two, liquidity is a word that is used to describe how easy it is to turn something into cash, okay? So those are the two ideas I need you to walk away from today's discussion, and we'll continue the discussion tomorrow. Oh, that's okay. All right, ladies and gentlemen, we are on what day? Oh, day 2, week 2, in our discussion about the Civil War. And today we are discussing total destruction. Bum, bum, bum. So, the South was losing. It's towards the end of the war. It's 1863. They knew that they were on the way out, but they didn't want to give up. The Southern people in general and their leadership had this crazy notion that they would not be beaten, that they would rather die fighting. And so in the North, this was becoming more and more obvious. And so General Ulysses S. Grant and General Sherman both decided that they would begin a campaign of total destruction. When they would come around to a place, it was important that they really, really, really drove home the meaning of a continued civil war. It was time for the Civil War to be over, and the South still continued to hold out. They would not accept the inevitable truth that was coming to them. And in order to get them to accept, Sherman and Grant and all the Northern generals began following this idea of total destruction. When they would come through to a place, they would destroy it utterly and completely. They would burn every house to the ground. They would kill every farm animal. They would burn every field so that there was nothing to come back to. And they weren't doing it because they hated them. They weren't doing it to be mean. They were doing it so that the South would understand that it was time to end the war. And this campaign of total destruction was truly awful. That happens a lot. If you study wars, kids, a lot of times a defeated army just doesn't want to give up. A defeated army just wants to continue and keep going.
Blow up all the bridges.
Yeah. And in fact, General Grant had to deal with it with President Lincoln, and President Truman had to deal with it back in 1946 during the Second World War, when the Japanese just wouldn't give up. And so the way that Truman dealt with it was he also made a campaign of total destruction in his use of the atomic bomb. And when we did that in World War II, we didn't just drop one bomb, we actually had to drop two before the Japanese gave us total and complete surrender. And so since nuclear weapons had not been dreamt up back in the Civil War, this total destruction, this campaign of total destruction, where it's a scorched earth policy, everything is burned, everything is killed, okay? It had to be done. And so General Sherman, in something that is famously known today as Sherman's March to the Sea, burned everything to the ground. I think I believe it was from Atlanta. Do you remember, Miss Kimmy, Sherman's March to the Sea? I thought it went from Atlanta all the way to the coast.
It went to the Gulf of Mexico, didn't it? Down
Something like
out
that.
in below New Orleans.
It was like 100 miles or something more than, I don't know. You guys can watch the Khan Academy video. I'm tired right now. I've been working all
There
day.
you go.
So, but Sherman's March to the Sea was many, many miles of just complete and utter destruction. Nothing was left.
Burned
And so,
Atlanta.
yeah, it burned Atlanta to the ground. It was, for those of you who remember, the Civil War almost started back, I think, in the 1820s, when John C. Calhoun tried to get South Carolina to leave the Union. And remember Andrew Jackson, he threatened to completely wipe the state off the map. He was like, I'm going to mobilize the army, and we are going to take you down, and we're going to completely destroy you, okay? The total destruction policy was the realization of Andrew Jackson's original threat. And after seeing the destruction that the Northern armies left in the South, General Lee had no choice but to surrender. And so this brings us to the end of the Civil War. Oh, do your Khan Academy assignment.
Do your Khan Academy.
All right, kids, we're in literature, week 2, day 2, and I think you just read the chapter Gulf Stream. Let's keep it real brief. The Gulf Stream chapter is kind of a dramatic chapter. This is the chapter in which we see Captain Nemo kind of like falling into what you could describe as like listlessness or even depression. In the last chapter, his buddy was like not eaten, but like killed by the giant squid, and he's just kind of loses his motivation, right? And so Aronnax actually approaches Captain Nemo and asks for their freedom. And that asking of the freedom in the Gulf Stream chapter really kind of changes the dynamic. It's never the same again. And so they have kind of this weird, tense argument, and then Captain Nemo he doesn't storm off, but he just kind of walks away and it's like, I don't want to talk about this anymore. And if I remember correctly, Aronnax is like, well, you won't let us leave, but you never said anything about us running away. And Nemo's just like, well, I guess not, you know. So the whole thing is kind of weird, but it addresses kind of the place where the captain's heart is at, because the captain is kind of going through grief from losing his friend, right? So the next chapter is a bunch of coordinates. Let's see here. I have to read it because I don't remember it. It's 47 degrees, the one that starts 47 degrees, okay? So that's your reading for tonight, and that is your literature for the day. Mm-hmm. Hey, welcome back to science. This is week 2, day number 2. Now, in week 2, day 1, we discussed Newton's first law of motion. And to kind of paraphrase it, it is objects at rest tend to stay at rest, and objects in motion tend to stay in motion. And both of those things are true unless those objects are acted upon by an outside force. Okay? So Newton's first law, objects in motion tend to stay in motion. Objects at rest tend to stay at rest unless they're acted upon by an outside force. Okay, so let's get to today's lesson. We are learning about Newton's second law. So we're going to do a little bit of reading. I have a few silly videos to show you that pertain to the reading, and then we're done. You have some questions, okay? I should recall or recount that all of the questions for science for the week are put into the day 1 packet, and so if you don't have those, you can go back to day 1 and download all of your science questions for the week, and then after today's lesson, you can get started on your next set of questions. Okay, let's get to it. So, on a sunny afternoon, you are babysitting for 2 boys who love wagon rides. Soon you find that they enjoy the ride most if you accelerate quickly. They shout, "Faster, faster!" And after a few minutes, you sit down in the wagon to catch your breath. If the smaller boy takes a turn pulling, but finds that he can't make the wagon accelerate nearly as fast as you can. How is the acceleration of the wagon related to the force pulling it? Okay, so again, that is the question we're looking at here. How is the acceleration of the wagon related to the force pulling it? How is the acceleration related to the mass of the wagon? So that brings us to Newton's second law of motion. Newton's second law of motion explains how force, mass, and acceleration are related. The net force on an object is equal to the product of its acceleration and its mass. Okay, there's a picture of the boy trying to pull the babysitter and the brother. Okay. Oh, here we go. You can increase. How can you increase the acceleration of the wagon? Look again at the equation for acceleration. Oh, did we skip a page? We skipped a page here. Okay. I'm sorry. The relationship among the quantities force, mass, and acceleration can be written with the equation force equals mass times acceleration. People often refer to this equation itself as Newton's second law of motion. Force equals mass times acceleration. With any equation, you must pay attention to the units of measurement. When acceleration is measured in meters per second, and mass is measured in kilograms, when acceleration is measured in meters per second, okay? This is an important distinction that I did not get to in last week's video about the Newton, okay? So I need to emphasize this now. When acceleration is measured in meters per second, or meters per second squared. Oh no. Sorry. And mass is measured in kilograms. Force is measured in kilograms times meters per second. This long unit is called the Newton, in honor of Isaac Newton. 1 Newton equals the force required to accelerate 1 kilogram at a mass at 1 meter per second, okay? So this is a Newton right here, okay? This is the scientific equation for a Newton. A student might have a mass of 40 kilograms. Suppose she is walking and accelerates at 1 meter per second squared. You can easily find the force exerted on her by substituting mass and acceleration into the equation. So the student is 40 kilograms, so it's about 88 pounds, okay? And she's accelerating at 1 meter per second squared. So this gives us 40 newtons, okay? Because 40 times 1 meter per second squared, and again, 1 kilogram at a meter per second squared is 1 Newton. So 40 kilograms at 1 meter per second squared is 40 newtons. Sometimes you may want to write the relationship among acceleration, force, and mass in a different form. Okay. Now, for those of you who know like pre-algebra, okay, we're taking this equation up here, Force equals mass times acceleration, and we're just dividing both sides by mass, okay? And that gives us acceleration equals force divided by mass. This form is found by rearranging Newton's second law, okay? All right, so here, let's take a look at this, and then I'll show you the videos, okay? Now, a lot of this is actually super intuitive, right? You have your force divided by your mass, which gives you acceleration, okay? Your force divided by your mass, which gives you acceleration, okay? If your mass is too big, then your acceleration is going to be super slow. Oh, where are we here? Where did I go? I'm looking for myself. There I am. Okay, that phone call messed me up. So acceleration equals force over mass, and so mass is the denominator. So if the mass is too big and the force is too small, then the acceleration is going to be really slow. Let me say that again. According to Newton's second law, acceleration equals force divided by mass, okay? If the force is too small and the mass is too big, then the acceleration is really, really slow. One last time, okay? Acceleration equals the force divided by the mass. If the mass is too big and the force is too small, okay, the acceleration is going to be very slow. Let's watch a video that illustrates this point, okay? So we're going to watch this video here. Same guy as the other day. He's the man who is a total grown adult who just plays with cars as if they were toys, okay?
And go for round 2.
So he is pulling with this tiny car. So this little car only is 80 horsepower, and with it he's pulling this giant trailer, okay?
That is how squatted the car. All right, we're starting up the Ferrari right here. We're just gonna send it. First gear. Send it. He needs bags. We did it! We just made history. Forget the man landing on the moon. We just pulled a gooseneck with an 80 horsepower car.
Impressive. By the way, I found out what the phone call was. Whoops, what's this? The phone call was the pizza guy. I guess when they deliver pizza now, they just leave it at the door and then they call you on your phone when you're trying to teach a science lesson. So, as you saw, the little tiny car was only 80 horsepower, and it was able to carry that entire trailer, but not very fast, because acceleration equals the force divided by the mass. And so the force of that 80-pound car was not very big, and the mass of the trailer was huge. And so it went very slowly, okay, because of, again, Newton's second law. I love how this guy is able to help us illustrate Newton's laws by the silly things he does. Okay, let's move on in the reading, okay? So again, acceleration, force over mass is just rearranging the law. A 52-kilogram water skier is being pulled by a speedboat. The force that causes her to accelerate at 2 meters per second squared. Calculate the net force that causes this acceleration, okay? So she is 52 kilograms, or he or she, I guess it doesn't give us the gender, right? Oh wait, it does, it's a her. Okay, 52 kilograms, okay? If this were only 1 meter per second squared, this would be easy. It would be 52 newtons, okay? But it's not 1 meter per second squared, it's 2 meters per second squared, so it's double 52 newtons, okay? So as you see down here, we have force equals mass times acceleration. The mass is 52 kilograms, the acceleration is 2 meters per second squared, and so 52 times 2 is 104, so 104 newtons. The answer tells you that a net force of 104 newtons is required to accelerate the water skier. This is not a large force, but it does not include the force that overcomes friction. So, what is the force, the net force on a 1,000 kilogram elevator accelerating at 2 meters per second? Okay? I'll let you stop and think about that. A 1,000 kilogram elevator accelerating at 2 meters per second. If you're thinking 2,000 newtons, you are correct. What net force is needed to accelerate 55 kilogram cart at 15 meters per second? Okay? So, in order to do this, we would need to take 15 kilograms times 15 meters per second squared. So let's go ahead and do that. Okay? So we have 15 times, was it 55, right? Yep, 15 times 55. And that gives us 825 newtons. Okay? So that'd be 825 newtons. Great. All right, let's get to the last page here of today's section. I love her pants. Isn't that great? All right, this is what life was like back in the 80s and early 90s, kids. Okay. How can you increase the acceleration of the wagon? Look again at the equation for acceleration. Acceleration equals force divided by mass. One way to increase acceleration is by changing the force. Okay, so you can change the force. The force gets bigger, the acceleration gets bigger. Okay? According to the equation, acceleration and force change in the same way. An increase in force causes an increase in acceleration. So to increase the acceleration of the wagon, you can increase the force you use to pull it. You can pull harder. Another way to increase acceleration is to change the mass. According to the equation, acceleration and mass change in opposite ways. This means that an increase in mass causes a decrease in acceleration. It also means that a decrease in mass causes an increase in acceleration. So to increase the acceleration of the wagon, you can decrease the mass. Instead of you, the boy should ride in the wagon. Okay? So she's pulling the wagon here, and we have the two boys in there, and they're having fun. But they want to go even faster, but the babysitter doesn't want to work harder, right? Theoretically, one of the boys could get out of the wagon, and the babysitter wouldn't have to increase her work, but she could pull faster. Because, again, we can either increase the force to increase acceleration, or we can decrease the mass to increase acceleration. Either way it works, okay? All right, so I'm going to end this lesson so I can finish the slice of pizza. But before I do, while I was looking for Creative Commons videos that I could show you for this lesson, I stumbled upon these gems, and I figured I'd share them, even though they don't mean anything. So, this guy is in a tractor. He is wanting to pull this very heavy load. It doesn't quite work. Whoa! Should have studied Newton's laws, my friend. I think he's okay, though, otherwise it wouldn't be funny. If he got hurt, this would be a not funny video. Oh, look, there it goes again. Okay? Too much mass, not enough force, no acceleration. If only they had studied your science class, kids. Is that the same guy? It seems like that might have been the same guy. Anyway, have a great one. Do your homework. And that has been week 2, day 2. Thank you much. This is Math Group 1, Week 2, day number 2. So Group 2, today we are going to review or learn something, if you haven't seen this before, that I think we neglected a little bit earlier. We have already talked about finding area for rectangular shapes like squares and other rectangles. We have talked about finding the area for triangles and how to do that. But today, something that I don't think we've gone into far enough is finding the area for trapezoids. So we're going to learn how to find the area for trapezoids in case we didn't already know. And then we are going to do a trapezoid area worksheet PDF for homework. Please take a photo of the PDF for your homework after you've completed it and send it to Mr. Barbero and myself. He is J. Barbero at DaVinciTree.academy, and I am Emerald at DaVinciTree.academy for credit. If you are not one of my students, don't worry about getting credit. Just give the PDF a try. Okay? All right, so let's go ahead and jump into it here. Let me move this to the side. So again, this is group number 1. We are on week 2, day number 2, and we are finding the area of trapezoids. Trapezoids. Okay, so we already know that area of a rectangle, okay, area of the rectangle is really straightforward. It's just the width times the length. So width times length equals area, okay? And then for the area of a triangle, triangle, okay? We take the base here, okay, times the height here, and we times it by 1/2. So 1/2 times base times height equals the area for a triangle, or a capital A area, I don't know. However you prefer. I don't think it matters too much, okay? All right, and then lastly, we have the area of a circle, okay? And as you should recall, okay, a circle, well, midpoint there of a radius, okay? This is the radius, and then across is a diameter. And so the area of the circle is area equals pi times the radius squared. And that gives us the area for that, okay? And so those are the 3 different kinds of areas so far. Okay, so let's start talking about the area of a trapezoid, okay? Area of a trapezoid. So the area of a trapezoid is interesting because it combines what we know. It combines the areas of rectangles and triangles. There we go. So the area of a trapezoid is a little bit of both, okay? We have to use our triangle skills and our rectangle skills. So let's go ahead and jump into a PDF very similar to the one that you're going to be doing for homework tonight, and let's work through a few of these, okay? Oh, why is that up? I don't know. Okay. Good, we're still recording. All right, so, let me just show you here. So I got my Netflix, got my photos, taking a lot of video of myself because of these lessons, and then you all know Hulu. Yeah, this is our graphing calculator for group 2. So if you're curious about what all these things are, that's what they are. All right, let's jump in. Okay, so here is the, I have an answer key here, but we're getting ahead of ourselves if we're looking at that. Okay, so let's go ahead and look at this right here, okay? All right, so, whoops, did not mean to do that. All right, so right here I want to show you, so we have, right here, okay, so we have one side is like 4 inches, the other side is 8 inches right there, and we know that it's 6 inches tall, okay? And so when we're taking a trapezoid like this, what we're going to be doing is we're dividing it up basically into 2, okay? And so we're dividing this up here into a rectangle, okay? So we're taking this as a rectangle, and then we're just taking 2 triangles on both sides here, okay? Again, trapezoids are just combining what we know about all of these things. Now, if we put this half of the triangle together with this half of the triangle, okay, we're going to get something that looks a little bit like this. Like if we cut them off and we put them both together, we get a triangle that looks a little bit like that, okay? Now, regardless of, I guess, how we do this, I guess, it's always going to be 6 tall, okay? So over here, this is going to be 6 tall, and it's going to be, let's see, it's going to be 4 here, okay? Now you might be asking, well, how do we get 4 and 6 for the triangle, okay? Well, when we look back over here, okay, we have 4 on this bottom end, okay, and we have 8 on this top end, all right? And so if this entire side here is going to be 8, and this side is 4, we just say 8 take away 4 equals 4, okay? And so what's left on this side and what's left on this side, combining them together, must give us 4. So that's why this triangle is 4 wide and 6 long, okay? And now all we have to do is we calculate how the area of our green rectangle right here, whoops, should be green, okay, there we go. And so for our green rectangle, we take the this top side here. Now this top side is not going to be 8, okay? We're actually taking this bottom side here because it's 4. Okay, we know the rectangle is 4 long on that side and 6 long on this side. So we take 4 times 6, and it gives us 24. Okay, and then we do the triangle part, okay, where we take them apart and we put them back together over here. And we know that the triangle is also 4 times 6 times, and then because it's a triangle, remember, we have to do 1/2. So 4 times 6, or 6 times 4 is 24, times 1/2 is 12. Okay, and so we would say 24 plus 12 gives us 36, just like that. Now, the unit is inches, and because it's area, it would be 36 inches squared, just like that. Okay? So again, when we're calculating trapezoids, what we're doing is we're actually disassembling the trapezoid into a rectangle and 2 triangles. That's all we're doing. Okay? Let's practice again on let's go to number 3. So it gives us, or let's do, pardon me. Which one's a weird one? Number 5 is a weird one. Let's do number 2, just for practice, and then we'll do a couple, okay? I don't want to leave you kids to this without showing you a couple examples. Okay, so here's my green rectangle right here. Okay, and my rectangle is 6 on the top and 4 on the side. So I have 6 times 4. 6 times 4 equals 24. Good. Okay, and now I'm going to put it in red again. Oh, sorry about that. Okay, got the red, and then red here. Okay, all right, so over here, this is 9 for the total right there. Okay, so that whole thing is 9. All right, and so this whole thing, sorry guys, my speaker is going a little crazy. That's why I'm repeating a little bit. I don't know if you can hear it. I hope you can. Okay, so I have 9 feet all over the bottom and 6 feet on the top. And you all know that 9 take away 6 equals 3. Okay, and so the base for my triangle for here and here would have to be 3. Okay, all right, so let me go ahead and make a triangle that represents that. So I have a triangle that'd be 3 down here. Oops. Okay, so 3 for the whole thing across. And then it would have a height of 4. Okay. Do you guys see that? Because again, I take this half and I. Oops. All right. And so I have 3 times 4 times. So 3 times 4 here gives us 12. And then times 12 times a half gives us 6. Okay? So this would be 24 plus 6 equals 30. So the answer here would be 30 inches squared. Just like that. Okay? All right, so that was number 1 and number 2. It looks like Christmas here with all my red and green. Okay. Let me show you an example here on number 5. So in number 5, my rectangle goes from here to here, and then up like this, over like this, here to here like that. And so my rectangle is 8 and 3, okay? So I can go ahead and start working on that. 8 times 3 gives me 24 inches squared. And then I only have one triangle on this one. It's right here. Okay? And I see, so if this is 3 down here, okay, and this is 7 up here, 7 take away 3 gives us 4. So this would need to be 4 right here. This is still 8, so it would be 8 times 4 times 1/2. 8 times 4 gives us 32. Half of 32 is 16. Now I have to take my 24 and add it with my 16, the green part and the red part. 24 plus 16 equals 40. So my area is 40 inches squared, just like that. Okay? I hope you're able to follow along. All right. Last one that I'm going to do with you, and then I'm going to leave you, let's see here. I need to double check. I don't know if we have a Khan Academy for this one to go with the worksheet, but if we do, I'm going to give that to you. All right, let's see. All right, so on this one, wait, it's green, right? Yeah. So on this one here, okay, here's my rectangle. Nice and green, okay? And so my rectangle is 5 feet by 8 feet. So I take 5 times 8, gives me 40. Nice. And I'd have my triangle here, good. My little triangle sliver up here, good. Okay, and so this is 10 feet over here, and this is 5 feet over here. Okay, and so you know that 10 take away 5 equals 5. And so that means that I have a distance here of 5 feet between this red part and this red bit up here. That's 5 feet. And then my height is still 8 feet. Okay, and so that gives me 5 times 8 times 1/2. 5 times 8 is 40. 40 times 1/2 is 20. Then I have 40 plus 20 gives me 60. So my area is 60 inches squared, just like so. Okay? All right, and so that's how we do area of a trapezoid. And if you have any questions, please let me know. Okay, again, email myself or Mr. Barbero. You can hit him up at jbarbero@davincitree.academy, and you can reach me at emerald@davincitree.academy. Where's my, oh, there it is. There we go, okay. Now let's see here, this is day 2. I'm gonna have a baby being born really soon here, so definitely, I think Mr. Barbero is going to be able to get back to you faster than I am. So I just wanted to give you all the heads up on that. Okay, I'm trying to record these a couple days ahead of time. If we have a Khan Academy link to go over this with you, again, I might save it for tomorrow, I might not. Just check the links in the bottom of the page. I need to decide after I stop recording. All right, see you tomorrow. We should be recording. We are on day 2 for group number 2. So what we're going to be doing for the next several days, we are going to continue doing what we did yesterday, except it's not going to be as long. Yesterday's walkthrough, just for group 2, was about an hour, which killed my upload speed because I had to upload that whole video. And I'm sure that it was boring for you. So we are going to reduce the number of problems. So yesterday we had 1 example problem and 6 problems that we worked through together. Today we're going to be doing 1 example and 5 problems to work through together. We're trying to get them through them quicker. And then tomorrow we're going to do 1 example problem and then walk through 3. And so tomorrow is going to be day 3. And then on day 4, you all are going to get your own word problem and own word problems, plural. And I need you to solve them with the substitution method, the elimination method, and with the graphing method. So you have to do all 3. So that's kind of the agenda. And then on Friday, we have a review of just solving systems without using word problems. We are spending a whole week of time on this idea of using the solutions or solving for systems of equations and doing word problems because it is something that needs a lot of practice. In a lot of math books, there's only maybe a day or two devoted to this, and that's not right because this is a foundational skill to be able to solve a system of equations for to be able to create a system of equations for real world problems and then solve it is super important. And that's like one of like the keystone things for algebra 1 and even in algebra 2. This is super important. So that's why we're spending so much time on this. Okay. All right. So let's get to the lesson. I will stop just soapboxing to you guys. He's monologuing. It's like a villain. All right, so group 2, day 2. Remember, okay, for doing the word problems, if you don't know how to do them, try to write a verbal model, assign your labels, okay, use those labels to write a linear system and then solve. The methods that we have, this first one kind of stinks, so don't use it so much, guess and check. Nah, okay, so we can either graph, substitute, or do elimination. Okay, that's that. Let's get to the example. The cash register wasn't working. You are the manager of a shoe store. On Sunday morning, you are going over the sales receipts for the past week. They show that 240 pairs of walking shoes were sold. Style A sells for $66.95 and style B sells for $84.95. The total receipts for the two types of shoes, the two types were $17,652. The cash register was supposed to keep track of the number of each type sold. It malfunctioned. Can you find out how many of each type were sold? Okay, and so right here we have our verbal model. Okay, so with the boxes with the verbal model, down here we assign labels. Now when I do the labels with you guys, I usually just write the numbers on top of the verbal model. You can do it either way. We turn it into a system of equations here. So we know that the number of shoes sold was 240. So the two kinds, the x plus y equal 240, right there, boom. Okay, and then at the bottom here, we actually have specific dollar amounts. I apologize for my dogs barking in the background. Let's see here. Down here, using the substitution method, you can solve the first equation for x equals 240, take away y, and substitute 240, take away into the second equation. After simplifying, you will obtain 8y equals 1584, and solution of two pairs, blah, blah, blah. I am so sorry. Let me pause this video here. It sounds like someone's at my door. Okay. Hello again. It looks like my dog was just barking at the mailman. Sorry about that. Okay, let's keep going. All right. Okay, so we just went through this here, right? And again, you can see like the verbal models and everything else. Okay. Let's see here. Let's get started with the first problem. Okay. The total time for a two-member team in a 5160, 5,160 meter relay race is 16 minutes. Whew, they're fast. The first runner on the team averages 300 meters per minute, and the second runner averages 360 meters per minute. How many minutes did the first runner keep the baton before passing it to the second runner? Use the following verbal model to help answer the question. Okay, good. So we have this verbal model. So time for the first runner, time for the second runner, total time. Okay, so ladies and gentlemen, I want you to follow along. So take a moment and write down the verbal model. I'm going to copy it over to my iPad over here so we can start working on this, okay? That's your time for. Okay, there we go. All right, and then the second one is distance. Okay, here we go. This is kind of my not so nice version of that. Okay, cool. All right, so what is the question? How many minutes did the first runner keep the baton before passing it to the second runner? Okay, and we know that, so let's go ahead and assign labels. It's a 5,160 meter race, so the total distance is going to be 5,160. Cool, okay. Let's see here, it's in 16 minutes. So we know the total time is going to be 16 minutes here. Good. Okay. The first runner on the team averages 300 meters per minute. Okay. So the first runner, the distance, so he's averaging 300 meters per minute. Okay. And let's see here. The second runner averages 360 meters per minute. Okay, so the second runner is 360 meters per minute. Okay, all right, so we got to figure this out now. So first, for the time, we know it's only 16 minutes. And then second, for the distance, we know it's 5,160. So now that we have the verbal model laid out and we have the labels, we need to start putting together some our equations. So let's say that so we know that it's 300 meters per minute. So let's say that the first runner is going to be x, okay? So x equals the time for the first runner, and then y equals time for the second runner, okay? And then so that would give us x plus y equals 16 minutes. Got it? Okay. And then if we have x and y here, again x, again y, okay, that would mean that we have 300. So he or she is running 300 meters in 1 minute. So x is the number of minutes for the first runner, plus, and this one is running 360 meters per minute, and y is the number of minutes for the second runner. And we know the total distance is 5,160 meters. Okay? And so that's how we get from this verbal model, assigning labels, and then creating the system of equations. Let me double check, make sure this is recording. It's going to make me sad if it's not. Okay, good. All right, so now we have to figure out how we want to solve this. Okay, now we could use substitution or elimination. So when you're trying to figure out the method to solve, okay, when we have these guys up here and they both don't have any coefficients in front of the variables, that makes it so we can really look at elimination or substitution as two quick and easy methods to solve. Now, if these coefficients are real big, that makes me think that maybe substitution is easier. If these two coefficients are small, then elimination might be the better option, okay? But since these coefficients are kind of big on the bottom and we don't have any coefficients on the top, I think substitution is going to make our lives a little easier, okay? So, I'm going to take this first equation on the top here, and let's just solve for y. That shouldn't take too long. So we have x plus y equals 16, okay, or 16 minutes. Good. Line of fairness, just to be fair. We take away x from both sides, and that gives us y equals a negative x plus 16 minutes, okay? Now, since we have this in y equals mx plus b form now, we could even solve this by graphing, but we would have to put the other one in y equals mx plus b form as well. And so I am too lazy to do that at the moment, so we're just going to do substitution and plug it in. I think my little kid is knocking. Here, I'm gonna take off the headphones. Hey, sorry, I'm in the middle of recording a lesson, kids. Sorry. The pains of being stay-at-home, work-at-home dad, right? Okay. All right, so we're going to plug it into the bottom equation now for y. And so we have 300x plus multiplication 360 negative x plus 16, and this is minutes, okay, equals, I'm running out of space, 5160 meters, okay? All right, so we distribute here just like so, okay? And then we should get 300x plus negative 360x, because 360, okay, plus or times a negative x is negative 360x. And then, gonna cheat. Let's go ahead and use our calculator. Where's my calculator? Oh, there it is. Okay. I had to reset my computer this morning because it was getting upset from being on for too long processing video. Okay. There we go. So we have 5,760. Cool. Okay. So it's going to be plus 5,760 minutes equals 5160 meters. Cool. Okay, let's see here. So we can combine these two terms, and that'll give me a negative 60x plus 5,760 equals 5160 meters. Now let's stop and think a second here, okay? This is 16 minutes, is it not? It is 16 minutes, okay? And so this is in minutes, and this is in meters, okay? So what are we doing here? Is this going to work out? Because I'm mixing up my units right now, aren't I? Let's just go ahead and see what happens, okay? Now, again, I often tell you all that I'm not great at math, and so it's ironic that I'm teaching you math, okay? And sometimes you just got to see it through and see what happens and see if it makes sense, okay? And again, that's just me being honest. So we get negative 60x, take away, let's see here. So it looks here to me like this is going to be 600, okay? And if this is 600, oh, this is negative 600 actually, because this number on the bottom is bigger, okay? And so let's bring this over here, actually. Okay, so we get negative 60x equals negative 600, and I'm a little unsure about our minutes here, or about our units, but I do know that at this point we would have to divide by negative 60, okay? So that takes that out, and what this does is that makes that a 10, okay? So a negative divided by a negative equals a positive, so we'd have positive x, and then another negative divided by a negative would be a positive, and 60 can go into 600 10 times. So x would have to equal 10, okay? Now, I'm assuming that this is actually minutes here, okay? Or I should put MIN, minutes, okay? Because if we look up here, remember, x is the time, right? And so, like, again, referring back to this in the beginning, x and y are the times for each runner. And so I'm going to assume that x equals 10 minutes, okay? Again, I'm sure somebody out there watching this with their kids at home is like, oh, well, Mr. Roll, you messed up the units here or there. I don't see it right now, but that's okay. We're going to keep on moving. So if we plug in our 10 minutes back into here, okay, so x equals 10. If x equals 10, then y obviously has to equal 6, okay? Now what we have to do is we have to go back and we have to check this out. We have to make sure it works, okay? Does it work on the top equation? Well, it should, right? On the top equation, it should work pretty easily, right? Because we know right up here that if we sub in the 10 here and the 6 here, we get 16. So that's not a big deal, okay? So it works on the top. We need to check the bottom, though. Okay, so let's go ahead and check the bottom. So we have 300x plus 360y equals 5160. 300x plus 360y equals 5160. Nice, okay. X equals 10, y equals 6. All right, so now we have to plug them in. 300 plus 360 equals 5160. Okay, got to show every step here. Okay, let's distribute like that, rainbow it out. So got 5160 over here, nice, okay. 300 times 10 is 3,000, that's easy enough, okay. 360 times 6, let's cheat. 360 times 6, hooray, 2160. Did I get that right? Times 6, yep, 2160, cool. 2160, nice, okay. Now we have to add these guys up. 3,000 plus 2160, gives us 5,160, which just so happens to equal 5,160. Okay? All right, so we're correct. We got it. Okay? So for this problem up here, x really is 10, and y really is 6. Okay? And again, I apologize for my lack of understanding with the units here. The units are super important, okay, because otherwise, well, why are you doing this? But every now and again, I get confused too. Okay, so we solved the system, we got it right. Hooray! Okay, on to the next. That was problem 1. Let's go to problem 2. All right, Julio's white windowless van travels for 2 hours at an average speed of 40 miles per hour. How long must the van then travel at an average speed of 55 miles per hour to raise the overall average speed to 45 miles per hour? What is the total time traveled? Okay, this is a weird one, but let's get down the facts and think about how to do this, because we have to write out our verbal model first, okay? So Julio has this van, and it's traveling for 2 hours at an average speed of 40 miles per hour, okay? And so I think this 2 hours at 40 miles per hour, okay? What are the variables going to be? So we need to look for variables which are things that we want to know that we don't know, okay? So for how long must the van then travel? So how long must the van travel is something that we want to know that we don't know, okay? How long must it travel? And then what is the total time traveled? We don't know that either, okay? So we need to stop and think about this to figure it out. So again, this problem is weird. So let's see if we can just kind of get together with some kind of formula for this and try to do at least something, because this is, again, unbelievably weird. Okay, so let's clear some new space here. Okay, so we know that Julio's van was going for 2 hours at a rate of 40 miles an hour, which gives us 80 miles an hour. Got it, okay? And then we know that it's going to go for some unknown, I'm going to not use x here for multiplication. Let's use the dot for multiplication. There we go. And then we know for an unknown period of time, and so for x is unknown time, okay? For an unknown period of time, so for an x period of time, we're traveling at a rate of 55 miles an hour, okay? And then we want to hit 45 as an average, okay? And so remember, an average is the total number of something that you have, okay? And so for this one, we need to take, okay, so we have time at 45, time at 40, okay? And then we need to add that with time at 55, and that gives us total time. Okay, and then we have the next one is we want to make sure that we average 45 miles an hour,
And again, we're looking at some, wait, whoops, I'm still on the other, on the verbal model, okay? So we know to do an average, we need total time on the bottom, right? So total time has to be on the bottom because we're taking an average. On the top, we have, let's see here. How do you say this? I am struggling with this one. Okay, total time is on the bottom. At the very end, we want to have 45 mph average, okay? And on the bottom, we need total time. And then, so it'd be time at 40 times 40. You know what? I'm just going to write out the formula for this because this is a really weird problem that I'm struggling with. Okay, so we already know that Julio went 40 times 2 to give us 80 miles, right? So 40 miles an hour for 2 hours gives us 80 miles, all right? We know that an average requires division, and on the bottom we have all the time. So all the time needs to go on the bottom, okay? All the speed needs to go on the top, okay? And then when we're done, it should equal 45 miles per hour, okay? And so we already know that for 2 miles, he went at a rate of 40 miles an hour. So I'm sorry, for 2 miles. That's for 2 hours, he went at a rate of 40 miles per hour. And then we don't know what the rest of the time was that he went at 55. Okay? All right, and then on the top, so speed equals distance over time, right? Okay, so speed is distance over time. The bottom we have time, so it should be really all the distance. Okay, and so we already know that we have 80 miles to begin with. Okay, so at the top we have hours, miles. Okay, so we have 80 miles, okay, plus the 55 miles, because we're going at 55 miles per hour times x. Okay, because remember, x, not this x, sorry. X is the number of hours at 55 mph, okay? So we have the number of hours at 55 mph multiplied by 55 mph, okay? And then we have to put it back on the bottom too for our division, okay? And all this has to give us 45 miles per hour. God, there's got to be an easier way to do this. Unknown time. This is unknown time at 55 mph. Now this problem is super weird, and I'm only really identifying one variable other than total time. And so for a problem like this, where we are reasonably sure that this is a correct equation, okay, we have again 2 hours on the bottom plus x. And again, x equals the number of hours at 55. We have the number of hours at 55 times 55, okay? And then we have 80 because we know that 80 miles an hour is the total that we traveled over 2 hours, okay? And at the very end, all this needs to equal 45 miles per hour, okay? Now, this is not a system of equations. I am thoroughly confused, as I'm sure one day you will be too. In a situation such as this, okay, where we are totally and utterly confused about what to do, sometimes we have to fall back on the crummy method of solving, and that crummy method of solving is something that we continue to use here. Guess and check, aka plug and chug. Okay, let's do it. We're gonna just take a guess and see how it goes. All right, so right here, let's take a guess. And whenever we're guessing, we're always starting with easy things like 1, 5, and 10. Let's start with 1, okay? So if he goes at 55 miles an hour for 1 hour, okay? Keep it simple, 1 hour. Okay, we're going to start with 1 hour. Okay, let's plug it and chug it. So we have 80 miles plus, if we pop in a 1 up here, it becomes 55 miles times 1. Okay, on the bottom, we have 2 plus 1. We got to get 45. Let's see how this works out. Okay. All right, so on the top, whoops, I don't know why that happened. Okay, on the top, it's 80 plus 55, which is 135. Okay, and on the bottom, we have 3. Let's do the division. 135 divided by 45. Okay, so let's see here. That's going to be, what? No, that's not right at all. It's going to be at least 4, I think. Let's try that. 4 would be 20. 4 times 4 is 8. 16. Wait, no, that's not right at all. What am I doing? Should be 35 here. Or 3. I'm having a really off day, kids. I apologize. 15. 5. Holy cow on fire. Holy cow on fire. We plugged and chugged. We guessed 1. And we were right. 45. And this is miles over hours, so that's miles per hour. Okay? Equals 45 mph. Okay? Mr. Roll, how'd you do that? I don't know. Again, I put together, as best I could, a reasonable equation that I thought could answer the question. And because this question is kind of different, and I'm having to work with different variables that I'm not used to, I plugged and chugged, and I got it right. Now, if this was wrong, we'd have to figure out how far wrong we were, okay? If this was too high, like if it was dramatically above 45 miles per hour, in that case, what I would do is I would try like half an hour. If it was dramatically below 45 miles an hour, then we would have increased it to like 5 or 10 hours at 55 miles an hour. But it just so happens that we were right, okay? So again, having that plug and chug up there, we do have it for a reason, but it is kind of a reason of last resort when we're totally confused. Okay, let's keep on going. Oh, okay. So that was Julio's van problem. Oh, here's our next problem. Okay, Tegan and Riley go to a Mexican restaurant. Tegan orders 2 tacos, 3 enchiladas, and Riley orders 3 tacos and 5 enchiladas. Riley is hungry. Whew. One bill was $7.80 plus tax. The other bill was $12.70 plus tax. How much was each taco and each enchilada? Okay, so let's see here. Tegan orders 2 tacos and 3 enchiladas. Riley orders 3 tacos and 5 enchiladas. So Riley is ordering more than Tegan in every amount. So we can kind of assume that Riley's order is going to be the one that's $12.70 and Tegan's order is going to be the one that's $7.80. Tegan ordered less, therefore Tegan ought to pay less. Okay, so she has 2 tacos and 3 enchiladas. So we're going to use the letter T for tacos and the letter E for enchiladas. Okay, all right, so let's do it. So Tegan has 2 tacos, 2T, plus 3 enchiladas, 3E, and that equaled $7.80. Nice. Okay. We got $7.80. Okay. And then on our bottom system, this problem's a lot easier than the last one. Nice. $12.70 for 3T and 5E. 3T plus 5E. That's a gross 5. Okay. Equals, was it $12.70, I think, right? Yeah, $12.70. Cool. We add our little bracket there. That bracket's also gross looking, but that's okay. This is not art class or fashion. It is math. Okay, and so let's get this over with. All right, we have 2T, 3E, 3T, 5E. What would we want to use here? Well, earlier we used substitution, so I think we can use elimination. This is a good time to show everybody that when we're doing elimination, we can actually manipulate the top and bottom equation, okay? So Let's say that to do this here, let's get rid of our t's. Okay, so we're going to focus on getting rid of these t's here. Okay, so I'm going to multiply the top equation by, let's see here, let's multiply the top equation by 3. Okay, and the bottom equation, we're going to multiply, oh, you know what, I got to stop using the x's, it's too confusing. Okay, so on my top equation, we're going to multiply it by 3. On my bottom equation, we're going to multiply it by -2, just like that. Okay, all right, let's do that, and then we can combine them to eliminate some stuff. Cool. Okay, so on the top equation, if I multiply the whole thing by 3, I get 6t plus 9e equals, and then 780 times 3, let's cheat real quick. Okay, what is this? Oh, let me shut that. Let's see here. 780 times 3, boom, 23.4. Okay, I'm writing that on the iPad, you just can't see it. Okay, I should go back. Okay, 23.4. Okay, and then on the bottom equation, I have -6t. Good. And then let's see here, plus -10e. Okay, equals, and then this is just times 2. That's easy enough to do in our heads. We got a 14 there. We carry the 1, so that'd be 4 or 5, and then -2540. Okay, now we combine both of these here. And so these cancel out, so our t's are gone, so success, okay. 9e, take away 10e, gives us a -e, perfect. And then this is kind of hard to see, but it's a 2340. Okay, I'm going to invert these two. So this negative number is bigger, so this one's bigger and this one's smaller, okay. And so I know my answer is definitely going to be negative because the negative is bigger, okay? But to do the basic like arithmetic to solve it, I can stack the bigger number on top because really what I'm looking for is I'm just looking for a difference, okay? And a difference just means what is different between these two numbers and how different is it, okay? And so let's see here, that'd be 2, okay? All right, and so right here I got -e equals -2. And so now I just have to multiply both sides by -1. Okay. And then I get e equals 2. All right. And that should be $2. Okay. All right. So this one, again, a whole ton easier. E equals $2. Okay. And if e equals $2, I can plug in my $2 and find out what my tacos are. Okay. And so I'm going to go ahead and plug into this first equation. Let's do it nice and quick. All right, so 2t plus 3e equals 780. Oops. 2t plus 3e equals $7.80. Like that, okay. And then we just plug in the $2 there. We're all seriously donked up, so you're watching a quick edit. I plugged this guy right in here, this $2 free. I plugged it in for the tacos, okay? And here, let me show you where I messed up. So, yeah, I plugged it in for the tacos right there. It should not have been there. Okay, so we're just gonna. This is all gone. Okay, that's all messed up. So let's try this again. Hopefully on this take I can get it right. And I was just sharing in the other take that I am a little bit distracted, and so if your math videos are a little more long and wandering than usual, I sincerely apologize. My wife is just about to have the baby, and so life is a little weird for good old Mr. Roll right now. Okay, so I got to make sure that we're subbing it in for the right thing. E equals $2, okay? So we got to sub it in for E. Otherwise, like, I'll have to do another take, which will be time consuming and a little embarrassing. Okay. So I subbed in my $2, okay. 2t plus, let's see here, that'd be $6. Okay, equals $7.80. Nice, okay. So I gotta subtract $6 from each side now. Cool. And so I get $1.80 on one side equals 2 tacos on the other. Okay, and if 2 tacos cost $1.80, then I can assume that a taco is only 90 cents. Holy cow, this is wonderful. I gotta find out where Tegan and Riley are eating. Okay, so T equals 90 cents. Let's go all the way back up. T equals 0.9, okay? Now we always have to double check, so I'm going to double check by plugging in my results over here, making sure I got them right. So it's 3T plus 5E equals 1270. 3T plus 5E equals 1270. 3T plus 5E equals $12.70. A taco, as we calculated, is $1.90, and an enchilada is $2. All right, cool. All right, so let's plug it in and make sure it works. And then we will know that we got to bug Riley and Tegan and find out where they're snacking. Okay, I guess after this whole thing is over, and we can all go out and eat together again. All right, $2. Okay, $12.70. Okay. All right, so we got to distribute these guys out. All right, and so that gives us $2. And what is it? 9 times 3 is 727. So $2.70. This will be $10. Oh, that's easy. Okay, equals 1270. Okay, and we add these up, and yep, we get it. 1270 equals 1270. Nice. Okay. Sorry for all the embarrassing mistakes, but it looks like we got it. Okay. All right, folks, this has taken much longer than I thought. I'm just going to work through one more problem today, and then we're going to throw the other problems on. We're going to throw the other problems on tomorrow because this is taking too long. Okay, so we finished number 3 with Tegan and Riley. Let's go to next one, number 4. Allie is buying decorations for a birthday party. The before-tax total for 3 rolls of crepe paper is and 20 balloons is $11.40. Okay. After she starts decorating, she needs to buy more supplies. She buys 2 more rolls of crepe paper and 10 more balloons for $7.20. How much should each roll of crepe paper and each balloon cost? Whew. All right, another relatively easier one. Okay. So we have 3 rolls of paper and 20 balloons. Okay. I'll just say 3 paper plus 20 balloons equals, what is that, 1140? Okay, as you can see, I'm kind of doing the verbal model and the labels all at once. Okay, so she has 2 more paper rolls and 10 more balloons for $7.20. Okay. 720, what is that, 2 papers? Yeah, 2 papers and 10 balloons. Okay. 2 paper plus 10 balloons. Nice. Okay. All right. Let's just go ahead. We'll use P for paper and B for balloons. So we have 3P plus 20B equals $11.40. Nice. Okay. 2P plus 10B equals $7.20. Nice. Put the bracket in there. Ooh, that one looks a little better. Okay. Now we can solve. Oh, hooray, look at this. Okay, check out my B's, kids. Okay. 10 is a multiple of 20, and so I can use elimination and do this relatively easy. I'm going to multiply the bottom row by -2, and that should kind of be quick and easy. Okay. All right, let's do it. So I'm going to combine the top row with the bottom row equals 1140, and then I got to do my bottom row, multiplying the bottom row by -2. So -2 times 2p gives me -4p. Okay, -2 times 10b gives me subtract 10b. Negative 2 times 720 gives me a negative, whoops, 14. Ay, 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 ay. No. Okay. Negative 1440. Cool. All right, there we go. Okay. Just like before, you know that this cancels out, which is nice. Okay. I get a negative P over here. Okay. And then over here, I got to figure this out by subtracting. Got a 1440. Nice. Take away 1140. Also nice. 3. Great. Okay. And so, see, this one is bigger. This one is smaller, and if the bigger number is negative, we know the answer's got to be negative, and we know that the difference between those two numbers is 3. So negative P equals negative $3, okay? So we just have to multiply both sides by negative 1. That's a parenthesis. Negative 1, okay, and that gives us P equals $3. Okay, so we know what the paper equals now. So up here, P equals $3. Okay, now we have to figure out what the B equals. By the way, kids, if I do a Z, I put a line through it like that because when you're doing math and you have a Z variable, you have to have that. So whenever you see that without a line through it, it's always the number 2. Okay, all right, so I just got to plug it in and solve. So I'm going to take this bottom equation now, and I'm going to plug in my P equals $3. So I have 2P plus 10B equals 720. 2P plus 7, was it 7B? Is that right? No, 10B. I'm silly. Okay. 10B equals, it was 720. That's why I'm a little off there. Okay. All right. And again, just so I don't make another embarrassing error, P equals 3, and we don't know what B is. P equals 3, and B we don't know. Okay, so let's plug in $3 for P. There we go. 10B, $7.20. Cool. 2 times 3 equals 6. Okay, plus 10B equals $7.20. Okay. Have to subtract 6 from both of our sides here. Okay. And that cancels that out there. Great. So we get 10B equals $1.20. Okay. Divide both sides by 10 by 10. So B, oops, that's a gross B. B equals, looks like 12 cents. Okay. All right. That's supposed to be 12 cents. B equals 0.12 cents or dollars. Okay. There we go. And does that make sense? A balloon costing around 12 cents? I think that sounds about right. Okay. So a roll of paper is $3. A balloon is about 12 cents. I think that sounds about right. Okay. All right. I normally would plug them both in and check it, but this is going pretty long already, and yesterday's was unbelievably long. So let's stop it there. We just finished Allie's problem, so we have one more problem, number 5. If you want to try this at home, you can. This one is, I'll just share it with you. Amber's fabulous house has a rectangular yard for all of her crazy animals. The perimeter of the rectangle is 22 meters, and the perimeter of the triangle, excuse me, is 12 meters. Find the dimensions of her rectangular yard, okay? And so we have this to help us out with her crazy yard, and so we're going to be working on this tomorrow. And that is it for today. And so thanks for sticking with me. Sorry for all the errors.